My name's Neil Parkin, and my talk's going to be on optical research at BT. My alternative title for the day is what does an optical researcher actually do? And not many people know this. So I realise that not many people actually know this. If I ask my wife, she says I drink coffee all day. If I ask my kids, they say that I put lasers on freaking sharks. I don't know where that comes from. Always makes them laugh. If I ask my parents, they suggest that I fix telephones like the one on the right hand side of the slide. What does an optical researcher actually do? Could be any one of these three things. I'll let you guess which one is true that I actually do. But how did I get here? How did I get to where I am now? So I didn't take a standard route. I did an apprenticeship at Sellafield as an instrument mechanic, and as well as there, I was interested in how things are actually made, how they're designed. So I went to university, and I did a master's in electronics and optoelectronic engineering, and that's where I got my real interest in optics. And from there, I went to Hewlett-Packard, and I designed optical transceivers. So these kind of things, which are the optical workhorse of the network. These go on the end of every single fiber, and they're what convert optical energy to electrical energy and vice versa. Eventually ended up at BT, initially working in network design and working on DWDM networks, so dense wavelength division multiplexing networks, and then to optical research team. So not the usual route. So back to my title, what do I actually do at BT? Well, if you apply for a job at BT, this is the kind of thing you would see on the application, on the job advert. Lots of kind of quite dry titles, so things like business stakeholder engagement, collaboration project work, academic research, vendor engagement, involvement in international standards, intellectual property development, and internal research. So what do they actually mean? Because they're very dry on their own, and it's very hard to understand essentially what you would do on a day-to-day basis that these things are suggesting. So I'm going to go through three of these. I'm going to go through the ones in bold and try and give you a flavour of what that actually means to me on a day-to-day basis. And the first one is business stakeholder engagement. So there's two types here. First is a kind of pre-discussed future-looking research. So there's a piece of technology we know exists and the business wants to introduce it, and we carry out some research to make sure that it can be introduced in a seamless way. The second is we have a problem type of issue, and that's the one I'm going to take you through today. So this is when a problem can't be resolved by what we call the first, second, and third line support engineers. So those are the guys in the street and their own technical experts, and eventually it'll end up at research if nobody else can fix it. And this is when we get to play detective. So this is a real example, so hence the XXX at the beginning. So I'm going to read out this email I got, which is XXX trial results have indicated that our customers experience slow speeds when streaming video content and are unable to have access to full downstream bandwidth over the optical link. The customer is defaulting to their DSL-based broadband to receive a good service. So not good at all. When you get something like this, you've got to dig in further. You've got to find out what's already occurred on the network, what's already been done to try and resolve it, and so you can get an idea of what's going on. So this is when you're being a detective. You're trying to find out exactly what's happened, so then you can suggest something, some way of fixing it. So in this particular instance, all the optical powers are fine. They were within range. There was no alarms coming from the system. The fibre had actually been replaced twice to try and fix the problem. But we're getting slow speeds, but only in one direction. So now you're starting to get an understanding of what the problem may be, and you start to have your own suspicions. And what you have to do next is get the kit, get it in the lab, and try and reproduce the problem. So there's the same lab I'm sat in now. We have instruments here which are very sensitive, a lot more sensitive than the kit that's out in the field, and we can look at different parameters as well. And you usually have a few suspicions of what could be going on from what you've discussed with the engineers and the kind of system that they've been working on. In this instance, It's strange that we're getting some data through, but extremely little. But the optical powers are in exactly the region where they were supposed to be. So that to me suggested there might be some kind of interference going on. And I thought, okay, it could be multipath interference. And this is just a little diagram of what that can mean. So you could end up with an air gap, which would allow a light to be reflected back into the receiver, so that you end up with two wavelengths of the same light interfering with each other. Multipath interference combining to create coherent interference, so where you would get a small amount of data at the receiver, but there'd be a lot of conflict going on with that. And so I had to try and prove what I thought was happening was this. So it's a case of kind of trying to reproduce that fault in the lab with the same kind of equipment that's out in the field. And yeah, after a fair bit of testing, found out it was a very small component that plugs into the transceiver, and it was slightly out of tolerance. So sometimes it would work, but if you give it a little knock, it would create a very, very small air gap, which then allowed an extra wavelength of light to be reflected back into that receiver. So that's one small component out of the system that has millions. Once I found that and proved that that was the problem, I could feed that back to the business unit, and they could replace it with one that was intolerant, or replace it with a patch cord. So they were pleased with that, and we've managed to get a good result. So that was my first example. My second example is academic research. So like many of the postgrads listening on here, I spend a fair bit of time kind of reading papers on optical technology, but I also get a fair bit of time to spend collaborating with those universities that are developing the technology we're interested in. It's a two-way street. We get to understand the pros and cons of the technology they're developing, and the uni gets to understand how we would actually use that in real world, and if it would be of use to us. I've got two examples here. I've got multi-core fiber and I've got hollow core fiber. So the fiber we've been pulling in for the last 20 years is single mode fiber on the far left-hand side. So that has a 9-micron core, which is a glass core for the light to travel down, and we have 125 micron cladding. Now the central picture shows you multi-core fiber. Now that's the same outer cladding, 125 microns, so it's the same size, but within that 125 micron cladding, there are 7 cores. So now you've got 7 times the capacity. I'm working with an EU project called IPT Core with a Polish university and Polish vendor who's developing this technology. Now, the posh word for multi-core fiber is spatial division multiplexing, if you want to look up online, but it really does allow us to increase the capacity at lower cost. So imagine if you pull in one cable with one fiber in, you've just got that one fiber, but for the same pull, for the same civils cost, now you've got 7 times the capacity. So the critical point of this is that those 7 core multi-core fiber needs to be lower than 7 times the single mode fiber cost. And that's where we're working within this project, is to try and standardize this technology so that we have a large amount of volume. Everybody's designing the same type, so it lowers the cost to the point where it is usable. So really interesting technology. On the far right, we've got hollow core fiber. And as the name suggests, there's no glass in this anymore. Well, there is glass in the outer tubes, but the light is now transmitted in air. It's guidance in air. In single mode fiber, we've got total internal reflection where the light bounces around on the inside, but in this hollow core fiber, we've got guidance in air, which means that it's 30% faster than it is in normal silica. There's also other benefits here as well. So the fact that you're in air means that the power in the light is not transferred to a different wavelength. If we do that in glass and silica, then when you transmit light down there, the power from a single wavelength can be transferred across to another and create interference. We don't get that in hollow core fiber. Also, in hollow core fiber, we have quite a large amount of capacity for different wavelengths that we wouldn't transmit in single mode fiber. So we're working with the University of Southampton, who are world leaders in this particular type of hollow core fiber called NAMP, and we're working within a project called Air Guide Photonics there. Really, really exciting stuff. By the way, NANT stands for Nested Anti-Resonant Nodeless Fibers, and I think maybe Ardell later on will be discussing hollow core fibers, because it really is one of the standout technologies that was actually invented in the UK, I believe. So, my final example, the best bit, internal research. So this is where you can make your ideas real. You start with an idea, but first of all, you've got to get them from somewhere. So where do they come from? So everywhere, from talking to colleagues, conferences, workshops, staring out the window. I usually find mine from looking at a current piece of work and kind of flipping that idea around. So for this example, I've been reading papers on Raman amplification to remotely power a passive device. I kind of thought, well, reading this really expensive Raman amplifiers, and you put a lot of light down your fiber, why can't we use the existing light that's there, that's transferring our data, and harvest power off that without affecting it in any way? So that was my idea. But for any idea, you need a proof of concept. It's great having the idea, but you've got to try and prove that it actually works and it is useful. And get great support with BT for this kind of thing. So it's a case of design it, build it, and prove it works in the lab. So here we've got the circuit I designed and built. On the left-hand side, we've got a photodiode, which is harvesting the optical power from the line. Got an energy harvesting IC, which I took from a solar cell energy circuit. That's basically a switch. And then we've got a supercapacitor. And so my switch takes a small amount of energy from the photodiode and stores it in the capacitor. And keep on doing that until we've got a usable amount of energy in that supercapacitor. And then you can use it for something. In this instance, I was using it to power an optical switch. And yeah, circuit works. It looks good. But now the challenge is to show that it can be used for something useful. So that's, again, with BT, really good. We've got all the commercial equipment so we can test this kind of idea out. In this case, I wanted to prove that I could do something useful for fiber to the home. So here on the left-hand side, we've got a schematic. Might be a little bit complicated, but basically we've got on the top, we've got one FTT circuit, and then on the bottom, a second one. And I'm using my switch, which is in the purple, to connect the two together. So I've got a photodiode, which says is PD there, and it's detecting the amount of light on the circuit, and then if the light disappears because the fiber's been broken, it closes a switch and allows the customers on that top splitter, that 32-way splitter, to be connected to the bottom one, so providing resilience. So test this on real systems. On the right-hand side, we've got what's come from the real-time oscilloscope, which allows me to test all the timings on the circuit to make sure it works correctly. So yeah, once we kind of proved that the design works on a real system and a real use case, we need to get some benefit from that. So for my kind of work, it's publish, protect, and downstream. So publish, that's conferences like ECOC and OFC, and that's a case of kind of opening up a dialogue with the rest of the industry. Do you think this is good? Would other people be interested in it? Can we get more volumes and standardization around this kind of technology? Also, we need to protect, so if there's anything in there that could be patented, then we want to double check that, and we do that with our own internal patent attorneys. We also want to downstream, so that's to show to the businesses, rest of the businesses, that this is something useful that they could use. And it's always good if you've got a nice proof of concept demo with a shiny laser, even if it's not attached to a shark. It's really useful. So thank you for listening. I hope I've given you a flavour of working as an optical researcher at BT.